here says, okay, so this broadcast has started, so I guess I'm here.
You're good.
All right, so my name is Greg Deputy. Just in the way of quick introduction, I guess I'm here because I'm the author of BurnSim. In way of personal introduction, I was I graduated from high school and went to BYU studying chemical engineering with the intention of getting into the propulsion field. Actually ended up dropping out and getting pulled into an IT career, which is what I'm still doing today. So I ended up doing propulsion and rocketry as a hobby. BurnSim is a program that I wrote in my spare time. It's still something I maintain on my own. Started way back. Well, year 2000 is when it first came out. It was a program known as, it first was called KN-culator or KN Calculator. For those of us, KN was kind of using KN to develop motors way back in the early 2000s was kind of the norm for EEE and people doing research motors. And so that was kind of the first tool that I came up with for simulating where those curves would end up so people could build motors that would blow up less often. And that eventually developed into BurnSim, which took it beyond just simulating the KN, which is the ratio of propellant surface area to nozzle throat area over time. I'll do a quick walkthrough. I don't know. I have no idea how many people who are attending today have used BurnSim or been exposed to it. But to give let me share. I can go ahead and do a share screen and do a quick walkthrough. Let me see. There we go. So this is BurnSim. It's a few areas here to walk through how it works and what's important. Starts out over in this area here. I hope you can see my mouse moving, where you define the different grains of propellant that you have. There's a few details over on the upper right here for nozzle, your propellants, and there's actually a startup tab here which isn't currently enabled. This is some stuff I was playing around with to simulate startup transients and that sort of thing. But very basically, if you want to simulate a rocket motor in BurnSim, obviously the most important thing is to get accurate results is to have a characterized propellant. If you don't have that, there's the two default propellants that come with BurnSim called Slow and Viper. They're just a couple of pretty vanilla ammonium perchlorate propellants. The important numbers when you're putting in a propellant and your characterization numbers that really matter are number one, the burn rate coefficient, burn rate exponent, and those are pieces of the burn rate formula. Actually, I can throw that up really quick here too if it'll let me. I'm just going to switch to sharing my whole screen so you guys can see everything I'm doing. Share screen. Share my entire screen. There we go. So I see myself. Okay, so jumping over here. This is kind of the core of what BurnSim does. Using the burn rate formula to calculate how fast the propellant is burning. And now all that is, this is kind of a simplified formula, but all it is the burn rate coefficient times the chamber pressure to the burn rate exponent. And all BurnSim does is when you design them, let's go back here real quick so we can just see, okay, I'm going to add a propellant. I'm just going to choose a propellant, and I'm going to do a small, like a 29 millimeter motor or thereabouts, actually a little bit. We'll just say, pick a random grain length of 3 inches, 1 inch diameter with a quarter inch core. Oh, I'm sorry. Here we go. Quarter inch core, 1 inch diameter. No ends inhibited, so this is just a typical base grains. Other grains are available. Base grains obviously the most common, but there's a lot of other things that people mess with in here. And you just add a grain, and let's say there's 2 grains. And this just kind of gives you a 2D representation of the cross-section of the grain. Pick a nozzle size. We're going to say, just nozzle diameter, 0.2 inches. Exit diameter is going to be a little bit bigger, Just say 1, and you just start getting data. And what you're seeing over here is, I'll turn these all off and then just put them back on one at a time. This again is your KN, which was the beginning of the whole program, which is your ratio of propellant surface area to the throat area. And the reason that's an important number, it's an easy way to define where a propellant's going to basically work in a motor. If you keep it, you can, without having to go through the hassle of characterization, it used to be you'd mix up a propellant, you'd test it in motor. If it didn't blow up, you were happy, and you could figure out, oh, the KN maxed out at, in this case, our maximum KN was 450. So typically you can say, okay, this propellant ran at 450, it didn't rupture the case. As long as I design other motors that keep the KN under that, I'm good to go. And then later on, we wanted more than just doing the KN, so we added thing, where we can simulate the pressure, which in this case, we're heading up around 1100 psi, which is, for a smallish aluminum case is fine on the higher end. And then we also do some thrust calculations based on your nozzle dimensions to give you a simulated thrust. This is currently in pounds. I'm going to turn these off. So in this case, this is a pretty small motor, peaking up around 40 psi, or 40 pounds of thrust. And I apologize for all my English units. Like I said, it's that's just how I've been doing things forever. But we do support metric units in here as well. Anyway, so what's actually going on here is BurnSim is taking a look at your initial dimensions and everything of the motor, calculating the surface area, and starting with an initial, pressure, just atmospheric pressure, and it goes back to using the burn rate formula here. And it will calculate, basically, it'll start with, okay, the pressure is, 14 psi, atmospheric pressure, whatever, to calculate an initial hop. And it's got a little setting in here where you can choose your simulation sample intervals. This is in seconds. It's going to calculate how much propellant was consumed every 0.1 of a second. And it'll iterate through that, go through that over and over and over again. And as it's doing that, calculate how the dimensions of the grain are changing, how that changes the surface area, and that sort of thing. It's pretty straightforward. People have actually done this in the past with spreadsheets or done some approximations of it and that kind of a thing. When you're using BurnSim, I get a lot of questions a lot of time about, number one, what are these basic propellants in here? And I give out the formulas for them. Like I said, they're nothing special. There's something on the order of, a medium to low solids, pretty typical ammonium perchlorate propellant. Where things get more difficult is if you're doing your own propellants and you want to characterize them yourself. So there's that, you get a little more, your difficulty level goes up a little bit there, and you have to have access to some equipment. There's two pretty standard ways of getting the data you need to characterize propellant. Or to take a step back, what you need to characterize a propellant are burn rate and pressure data points. You want to know what the burn rate of a propellant is at a given pressure. If you have two of those data points, you can do a basic characterization. 3 or more are obviously better, but you need a minimum of 2. And in the industry, the typical way of doing that is with what's called a strand burner, which is a specialized piece of equipment which will burn a length of propellant in a chamber. It'll have measurement wires in that propellant, so it can measure the amount of time it takes to go from one point to another, to basically measure the burn rate. And the chamber will have mechanisms to maintain a specific pressure. So you can run multiple strand tests at different pressures and get a whole bunch of data points. For those of you going into the field and having access to some of this equipment in college, we'll probably get some hands-on with that potentially, and that's cool. For someone like myself who's a hobbyist, that kind of equipment is a little bit out of our reach. But there's a second method where they call it's often called a ballistic test motor, which is basically a large, heavy-walled motor that's an end burner and will burn essentially a piece of propellant like the shape of a hockey puck, a really big end burner. And so the purpose there, and you'll have a pressure transducer in there to measure pressure. So in a perfect world, you'd have like a hockey puck that's 1 inch thick, all the, one surface that burns, the rest of it inhibited. You have a pressure transducer in there. You can light that motor. You can measure the pressure in there, and you can control what you're going to end up with as nozzles. So you do one pressure test with a large nozzle, and you'll get 1 data point, and do it again with a little bit smaller nozzle, get another data point, and you get your stuff to characterize your propellant. And then with that data, you can do a couple different things. There is, I'm going to take you to an ancient website here. Hamrock.com is done by James Lanier. This site's been around for 20 some odd years, but nice thing about it is a very straightforward procedure for doing propellant characterization. Here's kind of a representation of that test motor that I was talking about. This one's actually a little bit more enhanced because it's got 2 different diameters of propellant. So you could do this with a single burn. If you the hard part here is getting this entire surface lit evenly. But ideally, you could do 1 single burn. You have, when this portion burns, you've got a 1 pressure, and you can, based on how tall that is, you know how long it takes, get your burn rate. Same thing, you'll see a transition to a lower pressure, and so you get 2 data points out of a single burn. But once you have that, there's some math that you can go through and use to calculate your ISP, well, your characteristic ISP, as well as your A and your N, and get that stuff. So there's also a spreadsheet that I put out that makes it another, if you run Excel, if you have access to Excel, Microsoft Excel, you can use this spreadsheet. This is another old website of mine, not BurnSim. This is my personal website that I can send these links out if anybody's interested. I have a spreadsheet. Let me open it really quick here. And what this spreadsheet lets you do is all you have to do is you get those data points. You get, oh, I have, my burn rate at this pressure. And you just have to plug the numbers in, and it will give you the A and the N numbers that you're interested in. You take those, you plug those into BurnSim. I'll have to wait for that to open. There we go. So as an example, this is a real straightforward thing to use, makes life pretty easy. If you get those data points, you have your, put in your test data, you have your, what pressure you got, at what burn rate, and the KN, which is, again, is just the ratio of the nozzle throat area to the propellant surface area. Here you see you got 3 data points, it graphs them for you, and it gives you these numbers. This is a representation of the burn rate formula. So in this case, your A value is the 0.0174, the N, your exponent is 0.4285. Take those numbers, plug them in the BurnSim, and you're off and running. The way that you plug those into BurnSim really quickly, so you've got, here's your burn rate coefficient right there, your burn rate exponent right there. Propellant density is also an important characterization number, but that's pretty easily measured. Yet another piece of software out there called, there's actually a lot of different versions of it, ProPep. That is a piece of software where you plug in the ingredients of your propellant, and it will give you numbers like your density and the C-star value, which is just another way of representing the characteristic ISP, which that's a measure of the amount of energy available in a propellant and how much it can, in the ideal world, push out. A couple other things in here in BurnSim. There's something that's called pressured varied properties, and this is something more specific to sugar propellants. They have a tendency to, for these numbers, your characterization numbers can actually vary at different pressures, which can make things more complicated. And ammonium perchlorate propellants are generally pretty flat, and you can ignore the changes there. But with sugar propellants, that can change more. So if somebody wants to simulate a sugar motor in here and they want to have their characterization numbers that vary based on chamber pressure, you have the ability of plugging in, You can add, a new value that says, here's all my characterization numbers. Oops, that was the wrong button. I need to edit. There we go. You can put in characterization numbers. You can say, between this pressure, this low pressure, and this high pressure, these are my AN ISB values. There's a few other things you see in here, like specific heat ratio and molar mass. Those are not currently used in the simulation. They're something that, again, are part of the startup transient and some other things where I was playing around with some thermodynamic calculations, some other things where these numbers come into play. But they're not used in the standard simulation. So BurnSim does a pretty good job of simulating a motor burn in where things start getting out of hand is in very high length to diameter ratio motors. So if you have a very long motor, what comes into play there is erosive burning, which is, like you saw the burn rate formula where we're calculating our burn rate based on the propellant characterization. Another factor that comes in is the speed of the gas moving through the motor, down the core of the motor. And what will actually happen is, as that speed increases, it actually compresses the flame front. Well, there's a lot of theories and a lot of explanations of what erosive burning is, but the short version is it's the enhancement of the burn rate of a propellant caused by rapid gas movement through the motor. And one of the mechanisms that's theorized there is how, as the gas is moving through the motor quicker, it compresses that flame front, which causes the propagation of the burn to increase, which increases your burn rate. The problem with that is increased burn rate means increased pressure, and what you can end up happening is a runaway where you'll end up with a case rupture. Experienced this personally, ran into that when I started doing longer motors, and everything simulates, looks like it should run just fine, but you have a motor on a test stand or a rocket on the pad, you hit the button, and it immediately goes boom. And unfortunately, the worst time for erosive burning is in the is in the very beginning of the burn, because that's when your core, like in a base grain, your core is the smallest, and you essentially have the fastest gas velocities moving through the motor. One way to measure that is what we call mass flux, which is basically a measurement of, I apologize, I forget off the top of my head, but it's basically how much gas is moving through how much space. And it's the higher that number is, basically, it kind of translates to gas velocity, or it's a representation of gas velocity. So the higher that number is, the more erosive burning potential you have going on there. And again, that's another propellant-dependent variable. Some propellants will have a increased propensity for erosive burning. Others will be more tolerant. In other words, some propellants will a little bit of your mass flux gets up to a level, and it'll impact the burn rate a lot, and other propellants it won't. And a lot of the reasons behind that can have to do with particle grain size in the propellant, ingredients, burn rate, enhancers, and that kind of stuff. Fortunately, in the short term, it's something you can, similar to KN, you can watch for where you start seeing burn rate changes based on mass flux. So if you can do some experimental test runs with motors, you do a series of motors where your mass flux is increasing based on the design of the motor, and watch for where the burn rate starts going out of line with your simulation. If you see that, you know at which point, using mass flux as a threshold, that your burn rate's going to get out of hand, and you can just stay under that. And one way you can keep the mass flux down or reduce your gas velocity is things like, you'll see motors with stepped cores, where the bottom grain will have a larger core and it gets smaller towards the top, rather than having the same diameter all the way down. Eventually, my goal is to be able to characterize and simulate that as well. That will involve, the problems there, number one, is characterizing erosivity in a motor, for a propellant. So one way that can be measured is to do partial burns of a motor, where a motor will be tested and then interrupted in the middle of the burn. Techniques for doing that involve explosively opening a case to try and extinguish the burn partway through, which is difficult. And the reasoning behind that is they'll go and look at expected burn, how much of the propellant was consumed versus how much is actually consumed, and use that to figure out how much erosivity is going on. A little bit easier way to approach that, or at least the way that I look at it, is to do where your mass flux is increasing as you go, collect data on those, and then compare the results to what is simulated. BurnSim does actually let you do some of that as well. You can take a simulated motor and import test data and then line that up against your actual collected thrust data, or not thrust data, but pressure data. So we're doing okay on time. I can try to think of where I have an example of that. I'm going to jump to another computer here really quick where I have all of my personal simulations and things like that. Let me get this stuff out of the way. And I'm just going to bring up BurnSim here. Join my wallpaper of rocket recovery. No, I don't need to do that right now. Yep, that's fine. Let me see if I have one of these motors. I believe I have test data loaded for. These are some 114 millimeter motors that I have done in the past. There we go. All right, so here we've got a 2-grain 114 millimeter diameter motor that I actually flew this years ago, but I had done some test stand runs and actually collected data. So you can see here I've got a data set that I've imported. If you're curious on how to do this, it's pretty straightforward. There's a tutorial for it on the website, but basically you just, if you have your data in a CSV or in a spreadsheet, you can actually highlight that data in Excel, copy it to your clipboard, and then import it in here. And you can also import CSVs. But I'll go over here to my graph lines and I can see here. Let's turn some stuff off here to make it a little clearer. Apologize for my small screen on this laptop. Okay, so here's our simulated pressure. Here is our imported pressure, which is, I got to go over here and tell it to show me the graph, the data. There we go. So this is fun, where you can actually see, okay, the green line is my simulation. I'll turn that on and off to make it visible. And the orange line is the actual collected test data from a burn. This is actually a pretty good example. This is a very well characterized propellant. The simulation and the test data line up really good. This is not always the case, and this if you don't have a well characterized propellant, you're not going to get a nice something that lines up this nice. And also, this, like I said, this is a 2-grain motor. Length diameter is very short or small, so there's not any erosive burning going on here, and so it lines up really nicely. An example of where you start seeing erosive burning, it will typically look like a pressure spike in the first part of the burn. That does, so you can, like I said, you can characterize propellant, figure out where your mass flux threshold is, where things start deviating from simulation, and stay under that. You can design motors to try and keep your mass flux low. You can also do a motor which is a very progressive burn, where the simulation has it starting out at a very low pressure, and what you are expecting to see is a erosive burning spike in the beginning of that, but you take that into account to keep your pressure within design limits early on. And so, I mean, there's several techniques to either deal with that. Like I said, ideally, I'd like to be able to simulate it, but I haven't got to the point yet where I can reliably characterize a propellant for its erosivity and then define that in a way that you could plug in here and say, okay, given an erosivity factor of X that starts at mass flux Y, and have it start simulating additional burn rate based on that. I've been thinking of ways to do it, kicking it around, haven't done it myself. And there's a lot of papers out there and a lot of research on erosivity and how to predict it, how to calculate it, that kind of thing. So a lot of interesting reading on that as well. Trying to think of what else might be interesting to talk about. Let me get back to.
Hey, Greg, while you're popping around, this is Steve. Hey, we've got a question over on the Q&A tab. And,
great.
It's when using a ballistic test motor, is it necessary that we use the end burning configuration, or can we use other green geometries?
Well, the idea, you don't want the pressure, or I guess you don't want the surface area to change during the burn. So if you could use a Bates grain that's optimized to keep your surface area as flat as possible during the burn. So I guess, yeah, the answer there is no, you don't have to use an end burner.
Yeah, he follows up with, and this is a question from David Vestal. If we can use other geometries, I assume we would use average pressure to determine the burn rate. So that brings me to wonder what an appropriate cutoff would work to give a accurate result.
Yeah, so the devil's in the details on this stuff, absolutely. And like I mentioned, like when you're using an end burner configuration, you're using they get big and it gets hard to light that surface evenly to get a clean burn, that kind of thing. And also when you get that data, you'll see you're not going to get, in a perfect world, you get a nice up, flat, down. If you get that, you've got great data, but that typically doesn't happen. You'll usually see you've got your igniter, and typically a lot of the time we've tried things like copper thermite and other things to try and get that burn to go, and you're going to end up with a pressure spike at ignition, and then it levels out, and then if it drops off, that is a good indicator that you got that whole surface lit all at once. If it kind of tails off, then that's usually an indication that you had more of a not a flat burn, but more of kind of a concave burn. So those are challenges that you end up having to try and find solutions for as you go. And it's other things too. You can put like using a strand burner. You can put burn wires in, thin wires at different points in the propellant, and measure that along with your data. And that can be used instead of just, the propellant was 1 inch long and took this long to burn. You can actually have different data points in there to measure, it went from I know the wire was at this point and at this point, and take your measurement there. So there's options. Another approach that is a feature in BurnSim that I'm playing with, it's enabled, it's very experimental, is you can take a motor and design it in BurnSim, and then collect your test data, import it into BurnSim, and then there's a feature in there, let me jump right back to it really quick, where you can characterize propellant, the magic button. And what that'll do, what it attempts to do, is it actually runs a whole bunch of simulations. It takes characterization numbers, and it's doing a whole bunch of simulations here, and you can see in the background the graph is kind of changing. What it's trying to do is try different iterations, and then at every iteration it measures how far the curve is from the actual data. And then it will continue to do that until it gets the closest that it can and say, okay, this is what I think your propellant number should be. And so this is something that you can use as a swag at, if you're in a hurry and you want to get something ballpark and you have some test data, you can use this feature to get in the ballpark. And it's, like I said, it's experimental, it's kind of fun, and you can do it with any motor. Obviously, the more simple the motor, the better. And you do not do it with a long motor. If there's erosive burning going on in here, then any results you get from this kind of an approach are going to be completely wrong. And like I said, it's experimental. It's buggy. It's throwing exceptions here. It is enabled though, so it's there if people want to play with it. But yeah, there's been a lot of different approaches to doing ballistic test motors to characterize propellant, because that's your first. If you really want to get some accurate simulations, that's your first step. You got to have garbage in, garbage out. You got bad numbers on your propellant, your simulations are going to be meaningless.
All right, we got another question here. It's about smoke grains, and when testing motors, should we static test with a smoke grain, and will it impact the pressure reading?
Oh, it absolutely will affect your reading. I mean, it's propellant; it contributes to the motor. What I personally do is, when I make my smoke grain, I try to. Well, you can do different things, but I like to have the smoke grain actually consist of 2 layers. There'll be one layer that's the same propellant that I'm using, and I'll target that thickness of that to match the web thickness of the motor, and that can actually be added to BurnSim as an additional end burning grain, so you can simulate for that. You can also, BurnSim will support simulating a motor with different propellants as well, so you could characterize your smoke grain propellant as a propellant, and it'll handle that as well. But it absolutely will affect your pressures. And in fact, I had a case where a friend of mine, had a 38 millimeter motor, ran great, decided to throw a smoke grain in it, and it KO'd because it added enough pressure to overpressure the case. So yeah, you definitely have to take that into account.
Very interesting, actually.
Yeah, the heat of those as well is something to keep in mind as well. If you have a long smoke grain that keeps burning, 5, 10, 15 seconds after the motor goes out, that generates a whole heck of a lot of heat and will really heat your case up as well. So another one of those things to keep in mind.
Let's see. Any more questions? I have a question about strand burners. I don't know that I've seen a commercially available strand burner.
I don't think there is one. It's things I've read about in papers. I've never even seen one in operation. But the concept is a pressure vessel that can maintain a given pressure, and then you can burn your strand in there and measure the actual burn rate. Excuse my cat.
That was perfect. Yeah. We're open for questions, guys. Anybody have any other questions, you can put it in the Q&A tab. Was there anything else that you were hoping to show, or anything else you would like to show everybody?
Nothing else coming to mind. I mean, like I said, this is a fun thing. I enjoy this as a hobby. I've been doing it I got hooked on rockets when I was an 8-year-old Cub Scout. And over the years, high power became a thing, got into that. Making your own motors, research, experimental, whatever you want to call it, became more popular. Was able to, get into that. And if it's not a way to save money, unless you're flying, NOP motors on a constant basis, you're not saving money. There's a lot of investment in equipment and that kind of a thing, but it's a heck of a lot of fun. Burning motors on test stands, lots of fun. Always keep the safety aspect in mind, especially if you're doing this stuff, there's the schools are good about, keeping that, but when you're doing this stuff on your own, I've had motors come off of test stands. I've had motors fly test stands. You don't always realize how much thrust is there, and you think, oh my, I got this big steel test stand, it'll be fine, and next thing you know, it's flying across the field. So, if you're doing that kind of stuff, safety first, always, the alive, uninjured, and out of litigation is always assume it's going to fail in the worst possible way. And if it does that, what's going to happen? If you're testing a motor in your backyard and it fails in the worst possible way, it's going to break off the stand, fly through your window, and burn your house down. And, if that's the worst possible scenario, it's not the right place to test a motor. Right. If you test that motor out in the middle of a desert, and the worst thing you can do, it breaks, flies off the test stand, explodes, sets everything on fire, and you end up with, a black spot on the ground. But, okay, maybe that's a little bit safer way to do a motor test.
Sure.
Yeah.
Hey, there are a couple of questions that have come in. If you had to model erosive burning, how would you go about it?
So what I'm trying to do, the way that I've been approaching that problem is, because that varies based on a propellant. Different propellants behave different ways. You need to have a way to, number one, measure that, So my approach is doing test motors that have short motors moving into long motors, so your mass flux is changing, and identify, look at your test data and identify, okay, mass flux gets to here, I'm seeing the burn rate accelerate this much. Mass flux is higher, the burn rate's accelerating more, and quantify that in some way. Which obviously I haven't nailed that down, otherwise I'd be doing it in BurnSim. But quantify that in a way that you can. It's probably gonna. What I'm thinking is going to end up being a burn rate enhancement factor that is based on your mass flux. So as the mass flux gets higher, it's going to increase your burn rate by this much. And then being able to simulate that also becomes more difficult because you have to take into account, okay, my burn rate increased and now my propellant regression is actually this much more, and that throws off. That also changes at different points in the motor, because at the very top of the motor, your mass flux is very low, and so there's going to be no erosivity. But at the very bottom grain of the motor, the erosivity is very high, and you're going to have more. So right now, BurnSim assumes the same regression throughout the entire motor. With taking erosivity into account, that doesn't work anymore. Now I have to keep track of, okay, the bottom, well, if I do it by grains, okay, the bottom grain is expanded this much, the core of the bottom grain, the core of the next grain is expanded a little bit less. But in reality, that's still only a best guess, because it's not doing, because the mass flux is increasing going down the motor, not just grain by grain, but, millimeter by millimeter. So it's realistically going to be turned into a three-dimensional simulation of your motor, because now that base grain, instead of just burning like this, it's now burning like this. And so things get really complicated really fast.
Yeah, well, he does follow it up with, is there any other software that does it, or is there some way we could, I don't know if he's offering, but I don't think so, but is there a way to add a plug-in to BurnSim?
Currently there's not. OpenRocket is an open source motor simulator, obviously I'm not in this for commercial. I do charge for the software, but I'm not making a living off it. It's not like a commercial game. Right. So OpenRocket technically, I guess, would be a competitor, but that you can get involved with. And I know they've been talking about erosive burning as well. So if you're interested in getting more into the software side of it, I would recommend looking at them and potentially participating there. And being an open source project, you would be able to do whatever you want with it.
Yeah, I know that some of the other schools are looking at augmenting OpenRocket with not more of the laminar flow type stuff, but at any rate, yeah. So that's what I thought the answer would be to the question.
I know there's other software that is like not commercially available, or it's used in the industry and in the schools, and I know there's software out there, but that's about as much as I know.
Well, this is sort of the perfect next question is do you offer licenses to Spaceport America Cup teams looking to try SRAD?
Actually, probably going to be just doing free student licenses here going forward pretty soon. I've had some schools approach me and want to buy like large chunks of licenses for classes and stuff, and we do discounted licenses for that. But I'm getting to the point where for education and students, I should just be giving it away. So watch for news on that soon.
Yeah, I know that we've had a little that sort of discussion in the past, and so I know you've been very generous with the college students, so thank you. And then there's one last question we have right now, which is for the strand burner. When you say it maintains a constant pressure, does that mean it has to release the pressure when the propellant burns?
Yes. Yeah, it has to. I've heard of ones that will bring the pressure up to the value that you want, and then you start the burn, and then it will vent the pressure at an appropriate rate to keep it at where you want it. So if you want to do a test at 500 psi, it will vent pressure to maintain it at 500 psi or 1,000 psi or 1,500 psi. And obviously that's a pretty complicated thing to have to, you know, or you're going to have some pretty good sensors and valves and those kind of things to do that. And you're not just dealing with room temperature gas, you're dealing with, you know, combustion products and stuff like that. So it's compared to a ballistic test motor, it's a pretty complicated piece of equipment.
Any other questions out there? Don't see anybody with any other questions. Just really want to thank you, Greg, for taking the time to present to the teams, and really like what you're doing. I've about a foot and a half into the SRAD motor development at this point. I've done a few. Use your software for the last 2 years, so you know, your contribution to the hobby has been great, and I want to thank you for it. And thanks for
my pleasure. I'm glad. Okay. I'm excited to see it being used.
Well, that's great. So with that, I think we'll stop the broadcast. And again, thanks again, Greg.
Okay, good to talk to you. Bye.
Yeah.